So this is Chapter 5, and Chapter 5 has everything to do with energy. And energy in chemistry, we look at lots of times, is the type of energy called heat energy. And heat energy at a constant pressure has a special name, and this is called enthalpy. Enthalpy is symbolized by the letter H, and absolute entropy of chemicals is usually difficult to find, but we can many times find the change in enthalpy that occurs. And the little triangle right here stands for change, and H stands for enthalpy, or heat at constant pressure. Sometimes people that have taken AP Chemistry 1 and Honors Chemistry, you've seen this heat at constant pressure written as a small letter Q. This small letter Q stands for heat, and sometimes you'll see a little P down here standing for heat at constant pressure. There are a number of different ways to find this enthalpy, or this heat. But before we look at those different ways, there's a couple of definition pieces you need to know. First of all, this class is all about how the heat changes from a system to a set of surroundings. The system is almost always the chemicals, or chemical, that we're studying, and then the surroundings is everything else. So the surroundings could be the beaker, could be the stir rod that's inside of the beaker, it could be the hand that's holding on to the beaker, it could be the air that surrounds all the chemicals that are inside of the beaker. Those are the surroundings. So when energy is given off from a system to the surroundings, we say that it has a negative enthalpy. This is known as an exothermic process. Thermic process. And then when heat is given into the system or taken into the system, it is known as an endothermic process. So think of summertime right now, because it's kind of warm out. When you go swimming in Lake Marion, or you jump into a pool, when you get back out of the lake or back out of the water, you feel kind of cold, or you feel cooler than what you did when you were in the water, or cooler than when you weren't wet. Well, this is because something called evaporation is going on. And evaporation is what many people call a cooling process. So if you look at it from the system's point of view, the system is the water. That's the chemical. And so the water is going to absorb energy, and therefore it would be an endothermic process. Where is it going to absorb energy from? It's going to absorb energy from you. And so it's going to take heat from inside of your arm right here. We'll give you a nice big fat arm. We'll give you some fingers too. And then if you're wet and there's water on here, the heat's going to go from you into that water, and then the water's going to go from liquid to a gas right here. And so the system is the water, the surroundings are you and the air, and therefore in this process we could write a thermochemical equation and say H2O liquid goes to H2O gas. And then for the enthalpy of this process, we would put a delta H. Whoops. I need a new piece of paper. I'm running out of room. H2O liquid goes to H2O gas, and the enthalpy change would be a positive, let's just make it up and let's just say it's a positive 100 kilojoules. This is because the energy would be put into this system, and then this system would change from liquid to gas. This is called a thermochemical equation. And the difference between just a regular chemical equation and a thermochemical equation is this piece right here. This delta H, or triangle H, or change in enthalpy value. This can be used stoichiometrically, just like we use the 1s or the 2s or the 3s or whatever the numbers there are in front of the reactants and the products. And what this tells us is for every 1 mole of liquid water, it would take 100 kilojoules of energy to change it to a gas. Remember, this is the change in enthalpy, and since it's difficult to know the absolute enthalpies of reactants and products. It just tells us how it changes from one place to another. So let's just say that we had an enthalpy of 200 over here. Well, at the end, we would have an enthalpy of 300 inside of these. Well, the change is 100, and you can see the difference between those two. That's what the delta H tells us. We usually never know these, and so it's not important to know, but it is important to know the change. We can use this thermochemical equation as one way to find the enthalpy, or the Q, for a process. It's related by the coefficients in the chemical equation. And of course, we'll see in some of the problems that are due today that they'll make tricky ways of asking you to find this. They might not tell you you have 1 mole of water. They might tell you you have 9 grams of water. Well, now you have to know go from grams to moles of H2O. And once you do that, now you can use the thermochemical equation right here to find the amount of heat in kilojoules, and then the number of moles of water would cancel. And so you could say for every 1 mole of this water, there's 100 kilojoules of energy that are put into the system to make that happen. So notice it's still converting to moles, but now the mole to mole ratio is not just from the coefficients, it's from the thermochemical information from that equation. So that's one way that you can find enthalpy, or you can find this delta H for a system. A second way you can find this enthalpy is by an equation using what's called the specific heat capacity. Whoops, capacity, that's a T in there, capacity. The specific heat capacity is sometimes symbolized with the letter C, sometimes a small letter c, sometimes a C with a little p down here, sometimes with a little s. But what the specific heat capacity tells us is the amount of energy in joules per gram degree Celsius or Kelvin that it takes to raise 1 gram of some substance 1 degree Celsius. For water, that's in its liquid phase, the specific heat capacity is 4.184 joules per gram degree Celsius. For a gaseous water, H2O in a gaseous phase, it's a different value. I think it's somewhere on the order of like 2.1 joules per gram degree Celsius. And so phases matter. Phases matter where you are. There's a table of these in your textbook. This gives rise to something known as the molar heat capacity. Molar heat capacity is simply joules per mole degrees Celsius, and converting between these two just means changing from grams to moles. We'll see that in a sample in one of your homework problems that you're supposed to do today. And then lastly, there's an equation that relates the amount of heat. If it's heat at constant pressure, sometimes you see a little P down here below the Q, and that's equal to mass times the specific heat capacity times the change in temperature, MC delta T, and the delta means change in temperature, which is temperature final minus temperature initial. And many of you have used this equation before, but this is another way, a second way, to find the enthalpy of a process or something that is changing temperature. The third way that you can find the enthalpy change of something is by using something called Hess's law. Now, Hess's law takes many tabulated reactions, or processes, like this one, H2O liquid goes to H2O gas, and then we made this up. Remember, this is probably not right. It equals 100 kilojoules, and then combines it with some other reaction. And then when you combine the reactions together, you can find the new delta H. There were 3 homework problems where you had to do that. And you can combine these reactions by adding them, subtracting them, or manipulating these reactions by flipping them around. And if you flip them around, of course, the value goes from positive to negative. Or by multiplying them by something. Since enthalpy is an extensive property of matter, it depends on the amount you have. So if you have 2 moles of each of these, well, you have to take the enthalpy and then multiply it by 2. Same thing with dividing by something. And then substances on one side and the other can cancel with each other as well. The last way, or the fourth way that you can find enthalpy, is using that's supposed to be a fourth, is using the thermodynamic quantities in selected substances. These are called enthalpies of formation. And so these have been tabulated by forming substances from their constituent elements, and then we can use these to find the delta H of any reaction or any process by summing, this big Greek letter right here means sum, the products' enthalpies of formation, and finding the difference between those and the reactants' enthalpies of formation. There were several homework problems where you had to do those as well. All right, any questions thus far on the review of Chapter 5? All right, if you would please then take out your homework for today, and we're going to take the next about 20 minutes and we're going to have you correct your homework. So please have a different colored pen or pencil because I want to see that you corrected it. And if you're watching this on the video, you might want to pause it now, come up with a different colored pen or pencil, and then your homework problems that you've done for today. And if you were stuck or you missed some or you weren't sure how to do them, now is the time for you to correct those and fix those. And then one thing, while you guys are coming up with those homework problems, I wanted to show you on the chemistry YouTube channel. This is the LSHS Chemistry YouTube channel. If you go to playlists right here, one of the most often viewed playlists is the problem sets worked answers right here. And so if you view this playlist right here, you can see problems are worked from all the different chapters thus far. And if you look down here at the bottom, here are the Chapter 5 problems. So if you want to go back and take a look, because I'm not going to go in a ton of detail about the problems right now, but I will work some. You can go back and you can watch each individual problem. You can watch me do each one and explain it as it goes along. So that's available for you just to help you along the way. So then, if you're stuck and we're distant learning and you're like, boy, I sure wish somebody could do this problem for me so I could understand it, there it is for you on the chemistry YouTube playlist. All right, everybody ready? Got your notebooks out? Got your homework out? Got a different colored pen or pencil? Here we go with number 39. That's the first one. Let's see if we can get a much better. There we go. Stop that. There we go. All right. The complete combustion of ethanol to form H2O and CO2 at constant pressure is the heat releases 1235 kilojoules of heat per mole. Write the balanced thermochemical equation. So first of all, we want to take and write the balanced chemical equation. So C2H5 plus 3O2 goes to 2CO2 plus 3H2O. And then what makes it be a thermochemical equation is writing the delta H and the equal sign at the end. And then that equals 1235 kilojoules, but we have to put a negative sign on there because it says it releases the 1235. It's an exothermic process. Okay? The energy is released, therefore it's exothermic. Give yourself +1 if you have this correct thermochemical equation. If you do not have the correct thermochemical equation, then correct it right now and then put +1. The second part, oh, by the way, we need a volunteer to keep track of how many points we have so far. I know what I'll do. Since nobody likes to identify themselves on WedEx, I'll keep a tally going. We have 1 point so far. 1. All right. Make sure that I do that. If I forget to put the tally down, then let me know as we're going along with problems. All right. Letter B says, draw an enthalpy diagram for the reaction. Well, enthalpy diagrams are nothing more than like a graph. And so the graph, you could make a box here, or you could just put a line here and a line here, and then you can draw an arrow right here and put a big E right here for energy, and energy increases this way. And when you look at the balanced chemical equation up here, you can notice that the enthalpy change is negative. That means energy is given off. So that means this part of the system right here would have more H, or more enthalpy, than this part. And so you put this part on the top of the graph because there's more energy, because energy goes up. And then you draw an arrow going down to this part of the equation right down here because it has a lower enthalpy. Draw an arrow going down this way and then say how much energy is released. So the part with more energy goes on the top, the part with less energy goes on the bottom. Put your delta H right there. That diagram is worth 1 point. We have 2 points so far. Any questions on 39? All right, the next question is number 43. I'm sorry, 41. My bad. I went one too quick right there. 41 says ozone. Let's see, it decomposes to O2 at room temperature and pressure according to the following reaction. So it gives us a thermochemical equation right here. And then it says, what is the enthalpy change for the reaction per mole of O3? Well, in the balanced chemical equation, you'll see that there's a 2 in front of the O3. For every 2 moles of O3, 284.6 kilojoules are released or given off. And so we could write a ratio or a fraction saying for every 2 moles of O3, 286.4 kilojoules are given off. But we want to know how many kilojoules there are per 1 mole of this. So you have to divide those two. And so when you divide that, you get negative 142.3, and then that's per mole. And many times you don't see the 1 written down here, but you can feel free to write the 1 down there so you know that's how many kilojoules there are per 1 mole of O3 that is decomposed in this case. Then letter B, which has the higher enthalpy? Well, you can see that the enthalpy is negative, which means that the substance over here is going to have a higher enthalpy than this substance right here. And during the change, some will be lost to the surroundings. And so the 2O3 has a higher enthalpy. We're not going to count 41 for a point, but make sure that you've got it down because there's easy questions on the test just like that one. Next one, number 43. I'll turn the page here. We'll pull it up on the screen. This one's got lots of parts to it, so it'll have several points to it. This one says, consider the following reaction. Is this reaction endo or exothermic? So I wrote it down up here, and then it has a negative 1204 kilojoules. Therefore, it is exothermic because energy is released. It's got a negative sign right here. From the reactants to the products, energy is given off. In letter B, it says, calculate the amount of heat transferred when 3.55 grams of magnesium reacts at constant pressure. Well, in the thermochemical equation, we're told for every 2 moles of magnesium, this amount of heat is released. Well, in this problem, we don't have 2 moles. We have 3.55 grams. So step number 1 is to take your grams and convert it to moles. That's what this part does right here. The converting to moles is worth 1 point. Put +1 on your homework problems and tally that as 3 points total so far. Then we can use the relationship that is actually stoichiometric from the balanced chemical equation. For every 2 moles of Mg, there is 1204 kilojoules of energy released. Notice how I put my moles of Mg in a position where it's going to cancel with moles of Mg. Grams and grams cancel with one another. And so then when we divide these two, multiply by 1204 and divide by 2, we end up with negative 87.9 kilojoules. That's worth 1 point. Showing all the work is worth 1 point, and then getting negative 87.9 is worth the point as well. All right, continuing on with letter C, it says how many grams of MgO are produced during an enthalpy change. So now it's kind of the backwards of the problem. We had this many kilojoules right here that were released. Okay, but in this case, we have only 234 kilojoules released. So start with your negative 234, put a multiply sign, put a line, and now take your relationship between negative 1204 kilojoules and put it in a position where it's going to cancel, and then put moles of MgO right here. And so it's just like doing a stoichiometry problem where we have a ratio between, or a fraction, between the kilojoules right here and the moles of MgO. this setup right here that I'm outlining in blue is worth 1 point. Now we're up to 5 points total for the homework. And then lastly, rereading the problem, it says how many grams. So now we need to go from moles of MgO to grams of MgO. And so 40.3 grams in MgO ends up giving you 15.1 grams of MgO. That's not worth a point, but make sure that you got the work down there so you know that, hey, the trick is the stoichiometry, converting from moles to grams, that you can do real easily. Last part of 43, how many kilojoules of heat are absorbed when 40.3 grams of MgO is decomposed into Mg plus MgO2? So now it's actually taking this reaction and flipping it around. And so it's going to be MgO going this way to make O2 into Mg. So notice that's the backwards. And when you have a reverse of the reaction, remember you're going to change the charge to positive 1204. Now, I'm going to do the calculation just like this reaction is written, and then at the end, I'm going to flip this equation, or I'm going to flip this sign back to positive. So 40.3, when in doubt, convert to moles. So put grams in a position where it's going to cancel, put moles of my new set of units. That's step number 1. Once I'm in grams, now I can relate my MgO right here to my enthalpy, negative 1204. This part right here, this fraction, is worth 1 point on your homework problem. That puts us up to 6 possible points so far. This fraction right here comes from the stoichiometry, negative 1204 to 2 MgO. Now, running these through on your calculator, you end up getting negative 1204 because the 40.3 cancels with 40.3, and negative 1204 divided by 2. Let's see. I think I should end up with 602, right? 1204 divided by, should be 602. Did I miss something there? Somebody post up in the chat if I missed something right there. Those two divided by each other gives me 1, and then 1 times 1204 divided by 2 gives me negative 602 kilojoules. Anyway, then since this is the backwards of the reaction, remember it's MgO decomposing to these two, I have to flip the sign of the H, and so it ends up being positive 602 kilojoules right here. That is the amount of energy that's absorbed. Okay, I rewrote the equation right here just backwards and then changed it to 1204 as well. Any questions on 43? We're not going to count any more points on there. Other than that, that was a lot of parts to that problem. There's one on the test exactly like that. All right, the next problem then, I believe is number 51. So I'm going to move this page right here. And then number 51 asks some questions about specific heat capacity. So specific heat capacity of liquid water is 4.184 joules per gram degrees Celsius. That's letter A. That's not worth a point. Letter B, though, says, what is the molar heat capacity of liquid water? So in determining the molar heat capacity, first of all, take 4.184 joules per gram degrees Celsius and know that I've got to go from grams right here to moles. So it'll be joule per mole degrees Celsius. So put grams in a position where it's going to cancel. Put moles as your new set of units. And notice how I put grams up here on the top and moles on the bottom because I want grams to cancel with the grams down here. Use your units as a guide. That's the number one thing in this chapter. And then 18 grams in a mole, I get that from adding up H2 and O on the periodic table. This is worth 1 point for having this fraction or this relationship in your homework. That takes us up to 7 possible points. Multiplying those two together, I get 70.5 joules per mole degrees Celsius. All right, letter C then says, what is the heat capacity of 185 grams of liquid water? So now I need to take my 185 grams and multiply it by the specific heat capacity, because then my grams will cancel with my grams, and I'll just have joules per degree Celsius. So multiply those two together, and I get 774 joules per degree Celsius. That answer is worth 1 point, which gets us up to 8 possible points. And then lastly, letter D, this one asks you how many kilojoules of heat are needed to raise the temperature of 10 kilograms of liquid water from 24 to 46. So this is a Q equals MC delta T, or an H equals MC delta T. You remember it's H when Q is at constant pressure, so sometimes you'll see a little P written down here below the Q. Sometimes you'll see it below the P too, C sub P, sometimes they write it for specific heat at constant pressure. So the mass here is 10 kilograms, or 10,000 grams. The specific heat capacity is 4.184 joules per gram degree Celsius, and then the change in temperature is final minus initial. Running those through the calculator, you end up with 904,000 joules, or 904 kilojoules. This work gets you 1 point. That gets us up to 9 possible points. I think I'm keeping track of them pretty close. Questions so far? All right, the next one is number 53, and this one takes and looks at the specific heat of something that's not water. It looks at octane, and it says how many joules of heat are needed to raise the temperature of 80 grams of octane from 10 to 25. So Q equals MC delta T, and here we have 80 grams of the octane. It gives us the specific heat capacity of 2.22 joules per gram Kelvin. And then we're changed 15 degrees Celsius, or 15 Kelvin, because remember the space between 1 Celsius and 2 Celsius and 1 Kelvin and 2 Kelvin are the same. And so you can use those interchangeably when you're looking at a change in temperature. So multiply those guys together and you get 2.66 times 10 to the third joules. That gives us our 10th possible point. Make sure you got the work down and the answer correct. All right, next one, letter B, asks which will require more heat, increasing the temperature of 1 mole of octane or 1 mole of water. So what I really need is I need the molar heat capacity, because I want to know how much heat is going to need to raise 1 mole of this. And I just did this in the last problem in number 53. I found the molar heat capacity of water to be 75.4. So I rewrote it right here. This is how much energy it takes to raise 1 mole of water 1 degree Celsius. Now I want to find the same thing for octane, and then I'll compare the two. And of course, whichever one takes more energy to raise it 1 degree Celsius would require more heat. So here's octane, C8H18, and its specific heat capacity is 2.22 joules per gram Kelvin. I want to go from grams to moles. So there's 114 grams in 1 mole. This work right here earns 1 point on your homework, so put +1 next to that if you have it. If you don't, please write it down. I added up 8 C's and 18 H's to get 114.2. The grams cancel with the grams, and my molar heat capacity is 254 joules per mole Celsius. So which one takes more heat to raise 1 mole of the substance? Well, obviously octane, and so octane would be the one that would require more heat to increase that by 1 degree Celsius, or a certain amount of temperature. Questions on 53. All right, now we get into some Hess's law problems. This is number 63. And on number 63, you have 2 equations that you're given right down here. And then here's your goal reaction right up here on the top, and you want to find that. And so here's my 2 given equations right here, 1604 and 2940. And I always like to start these problems by looking at the goal reaction right up here at the top. And then what you say is, where is P406 in one of the given reactions? Well, P406 happens to be on the right side, and I need it on the left. So I'm going to have to take this reaction and flip it around. And so then when I flip that reaction around, notice that I have a positive 1640.1 right here. So this is the backwards of this reaction right here. And then when I have the backwards of the reaction, it becomes a positive enthalpy. Now the second thing that I need is P4O10. And P4O10 is a product right here, so I'm just going to leave this reaction, the second reaction, exactly the same. P4O10 right here, 5 oxygens, P4. And then that stays the same as negative 2940.1 kilojoules. Now if I add these 2 reactions together and put everything on this side together and everything on this side together, I notice that some things cancel out. The P4s cancel out, 3 of the O2s cancel out, and I have 2 O2s remaining, and lo and behold, my goal reaction right here remains. P4O6, 2O2, plus P4O10. Then I add these two enthalpies together to get my enthalpy change for the goal reaction. All that work is worth 1 point right there. That's what Hess's law says, is that you can manipulate reactions, add them together, and then you will get a goal enthalpy for a new reaction. Questions about 63. 64, similar type problem, but now here's the goal reaction. And I always like starting with the goal reaction first thing, CO right here. Well, CO is right here. It's on the wrong side of this reaction, so I know I'm going to have to flip this reaction. And there's a 2 right here, so I'm going to have to divide this reaction by 2. Remember, when I flip the reaction, it's going to be positive, and then I'm going to have to divide that enthalpy by 2. And so I flip this reaction around, divided it by 2. Now there's a 1 here, there's a 1/2 right here, there's a 1 right here, and this is 2210 divided by 2. Notice it's positive right now. Rewriting this reaction this way is worth 1 point. We are now up to 13 possible points. Next, I look and I see that I'm going to need CH3OH right here. There's 2 of them right here. I'll end up dividing this reaction by 2 as well. And when I divide it by 2, I had 402.4 divided by 2. It's still negative because I didn't flip the reaction around. Notice this is divided by 2, divided by 2, divided by 2, divided by 2. That's worth 1 point for writing this reaction this way as well. That gets me up to 14 possible points. And then I add the 2 together, and I end up with negative 90.7 kilojoules. The canceling would work out pretty nicely here because the carbons go with the carbons, the 1/2 O's go with the 1/2 O's, and I'm left with my goal reaction of CO plus 2H2 goes to CH3OH. Questions on 46? There was a question that said, I didn't divide until after I added. Is this appropriate? You have to be careful with that. Make sure, we were lucky here because both of these given reactions needed dividing by 2, so it works out. But if only one of them needed dividing by 2, make sure that you divide the reaction first by 2 and then add them together. Because sometimes it might be that this one needs dividing by 6 and this one only needs dividing by 2. Well, then you can't just divide the whole thing by 2 at the end. Is that fair? Okay. Now we're going to go to 65, the last one of the Hess's law problems. This is on the top of the next part. Let me zoom in on that. So this one's a little trickier because we have 3 reactions, and then we have a goal reaction down here. And I started with the C2H4. I just started with that of the goal. You can start wherever you want, but I recommend starting with the goal reaction thing way on the left. I found C2H4 in the 3rd reaction right here. It was on the wrong side, so I flipped it around. And when I flipped it around, then I had to reverse the enthalpy to negative 52.3. Then I saw a 6F2, but I saw it in 2 reactions up here, so I'm like, let's ignore that one for now, and let's go on to something easier. The CF4 over here, I need 2 of those. I noticed there's 1 of them on the correct side, so I took this second reaction and I multiplied it by 2. So I doubled this reaction, therefore I had to double the enthalpy right here. So 2 times negative 680. And then lastly, I needed 4 HFs, and I saw I had 2 HFs up here, so I'm going to have to double this top reaction right here. So I multiplied it by 2 all the way through, and therefore I had to multiply the enthalpy by 2. And lo and behold, that gives me 4 Fs from this reaction, and it gives me 2 Fs from this reaction. So when I add them together, I'm going to get my 6F2. And so that one worked itself out really nicely, even though I hadn't intended it. This work right here of manipulating the reactions is worth 1 point. That takes us up to 15 possible points so far for the homework. When I add them all together then, I notice that my C's will cancel, my 2 H's will cancel, and the circled species are the ones that are in my goal reaction right here, and I end up with negative 2,490 kilojoules, I believe, for my final answer. Questions on 65. All right, we're almost done. Last couple of problems. 71 now. This one says the following is known as the Thermite reaction. This highly exothermic reaction is used in welding massive units such as propellers. This is actually a really cool demonstration, but it's super dangerous. Maybe sometime when we're face to face again, we can do the Thermite reaction in the fume hood. Using standard enthalpies from Appendix C, calculate delta H for this reaction. So here's the reaction right here. Here are my standard enthalpies of formation that are given on this sheet right here. Look under the delta H right here for each thing. And then it's always products minus reactants. And so my products are Al2O3 and 2Fe. Well, as you probably noticed when you're looking at the enthalpies of formation, if something is in its elemental form, it has an enthalpy of formation of 0. Look at H2 gas, 0. Look at F2 gas, 0. Those are the elemental formations. Lead solid, 0. Lithium solid, 0. And so iron, right here in this equation, is 0. So that's my first one, is having 2 times 0 here for iron. 2 is the coefficient in front, of course. And then Al2O3, I have to look way over here on this side, and Al2O3 is negative 1669.8, all kilojoules. On the other side of the reaction, now the reactant side, 2 times Al, that's going to be 2 times 0 again, because of course aluminum is in its elemental state, so it's an enthalpy of formation of 0. And then Fe2O3, that one you look up over here, and that one ends up being negative 822.16. This work is worth 1 point. That gets us up to 16 possible points. Do that math on your calculator, plus 1 point for having the correct answer, negative 847.6. 1 more point, 17 possible points. Any questions about 71? Last problem, 73. Using values from Appendix C, calculate the standard enthalpy change for each of the following reactions. So I'll do the first one. We have SO2 plus O2 goes to 2SO3. Now we're going to do products minus the reactants. Remember, it's always products minus reactants. And so if I look up SO2, it happens to be on the back, and I think it's over here. Let's see, sulfur-containing ones are down here. And that one's negative 395.2, and there's 2 of them, so I've multiplied it by 2. And then I subtract the reactants, and the reactants, of course, have oxygen in it, and O2 is going to be a 0 because it's in its elemental form. And then SO2, I look on the back here, once again, is negative 296.9. And then I multiply that one by 2. This work is worth 1 point. That gets you up to 18 possible points. I believe the answer ends up being negative 196.6. Any questions on 73? Letter B, the answer is 37.1. Products minus reactants. Same format, but you need these tables. So it's always handy to have these tables rather than go in your iPad book and go way to Appendix C to look them up. That's not worth a point. Hopefully you had a chance to practice enough of those to feel confident in them. That does it for all of the homework problems. That's the ones that were assigned from Chapter 5. That's barely enough, but if you can do those, you're in pretty good shape. If you can't do them without me watching me do them, I suggest you go back to some paired exercises. So you'll notice how, for example, number 43 has a paired exercise of number 44. Same type of problem, same difficult piece, but then it's together with 43. See those little lines right there? Give that one a try and see if you can do it without a lot of help. We have 18 possible points right here. Please put the number you got correct out of 18 at the top, and then take a picture of that. Put it into a Google document. Take a picture of all of your homework. Put it into your Google document. Share the Google document with anyone can view. And then go right down here to the homework today, and it says paste the link into this Google form right here. So very typical hand-in of that type of assignment. Put your period number, last name, first name. Paste your link right in there of your corrected homework. If you're watching this on video, make sure that you got it all corrected before you put it in there. and then you are golden as far as a 18 out of 18 grade. And hopefully it was helpful for you to learn some Chapter 5 things. Any questions about anything from Chapter 5? All right, I'm going to sign off from the video portion right now. I'm going to quit the video, and then people that obviously couldn't attend the live will watch it on video themselves.